So I'm going to go create a new project for this one. You probably already have a project created, so you don't need to create a new project. I'm just going to do that real quick. Call this new folder. This will be Lab1 128 22 at 0900. Not going to worry about that right now because I don't think we'll get to programming it anyways. I have a guide now on how to set that up. I sent it out yesterday. So we're going to begin by creating a new Verilog file. So you can file new and choose under design files Verilog HDL file, not VHDL. That's a different language. Verilog HDL. All right. So inside of Verilog, the important thing to know, one of the important things to know, is that everything has to be contained inside a module. And the way to think about a module, if you're thinking about it physically, would be like an integrated circuit. You have inputs, you have outputs, but everything else you define inside the module is a black box. So nothing else really knows about. So I'm going to go take this approach from, so in the schematic we built everything all in one. In this approach, I'm going to take the approach of creating two components, a multiplexer and then all of the connections. So I'm also going to create one more, so I'm going to go file new, I'm going to create one more Verilog file, and this one's going to be our multiplexer file. So this one will be called file save as, I'm going to call it multiplexer. This lab is simple enough you could do it all in one module, but it's best practice to try and separate things. Just like in programming, we're trying to separate out components. Alright, so now we're going to start with the keyword module. That's where we put all of our data goes in here. So the first thing we have to do in our module is we have to define our inputs and our outputs. So in a multiplexer, and specifically in this multiplexer, we're going to make it a 4-to-1 multiplexer, and then we'll have two of them, one for F0 and one for F1. So we'll have a 4-to-1 multiplexer, which means that we will get a select pin. So I'll call this input select. Input wire select. And then after wire, I'm going to call this 1:0 to say that that's a 2-bit wire. So I have an input wire select, and in our multiplexer now we need four. Yeah, we need four inputs for our X1, X2, X3, X4. So I will go ahead, and those are all going to be 1 bit, just 1 or 0 on the outside. So I will call this X1, X2, X3, X4, and if I was paying attention, I would have realized that I also need to put input wire in front of these. Input wire, input wire. The default assumption is wire if you don't put wire, but it's best to specify. It's just best practice. Because there are regs and there's bidirectionals and there's a few other types that you can use. Alright. And then a semicolon after that module. And then I like to make a new line there so I have some space to work, and then I'm going to type end module and another new line so that I don't forget to close my module. Okay. So should we do gate level modeling or assignment level modeling? They call it. I think they call it functional modeling in the lab. You want to do gate level modeling? Yeah. All right.
The one in your video, it kind of broke down how to format it. So.
All right. So let's go over gate level modeling then. So gate level modeling is good for simulation. It's not as useful for synthesization. So if you're synthesizing something and you're saying, I want to put this on my board and have it work, you don't want to use gate level modeling because it's telling the compiler not to do anything. It's saying these are the gates that you have to use. This is how they have to be connected. So the idea would be if you had a circuit, you were constrained on parts, and you designed this circuit and now you wanted to simulate it, then you would use gate level modeling to say these are my parts, these are how they're connected. Before I solder everything together, is this going to work?
Yeah. An assignment level modeling, where you would kind of do some optimization.
Yeah. So in structural modeling, or assignment modeling, we would say, I want this logic equation, and I want f to equal this. And then the compiler would go through and pick the most optimized gates to make that happen. So it's a different, two different, I guess, depending on what you want to do, you use one or the other, is what I'm trying to say. Okay, so we also need an output. I realize we don't have an output. So our output will need to be let me think about that for a second. So our output is going to be 1 bit because it's just going to be one of these inputs. So it'll be output wire F. Okay, so in that case, if we're going to do, we know we're going to need 8 AND gates because, 4 AND gates specifically. So, because we're going to use 2 multiplexers here. So we're going to say and F, because that's where it's going to go out of. And then we're going to say S0, comma, actually, I need to negate these first, don't I? Because we're, right, so I'm going to do not, let me think about this. All right, I need to make some kind of internal wire, just like we had in our schematic. I need to make some internal wires here. So I'm going to go something like wire not S0, comma, not S1. And that will give me those. That's where I will store the inverted version of S0 and S1. So I need some wires that will store the inversion. So I'm going to say not, and then not S0, and then S0.
So your S0 and S1 are your actual 2-bit select.
Yes,
right?
yes, that's what I've called. Oh, yeah. So, so here I've called them selects, and I guess here I need to call them selects. Thank you for catching that, because that should be select 0, and I'm storing it in not S0, the wire.
Okay.
So that's how the syntax works. Where do I want to store it? What do I want to store? Like, what are the inputs? Input on the right, output on the left. So then this should be not S1, and then select 1. Cool. So now I have my inversions. So now I can start with this. On this one here, it should be not S0 and not S1 because I've created these internal wires here, labeled them not S0 and not S1. So these, because they're not inputs or marked as input or output, they are internal. They aren't seen by the board or any other module. This is part of the black box that I was talking about before. I've just created a couple of wires here, and now I'm going to assign them to be the inversion of select 0 and select 1. Just exactly the way we did in the schematic, except that now instead of doing it with symbols, we're doing it with code. Alright, so now I can do my AND gates, and I can do AND F, S, or not S0, and not S1, and X1. And then AND is it?
So
It's
that would be your AND, like when you combine the other ones, it'll be your X1 is the wire that would come from your ANDing of A0 and A.
Yeah. So in this case, I've made a slight mistake here because F should not be the output. F should be only the output after we OR everything together.
Yeah.
So I'm going to delete that. But what we're seeing here is that I'm ANDing not S0, not S1, and X1. So whatever I pass into X1, if not S0 and not S1 are both true, then X1 will get passed to whatever I store it on.
Yeah. So for our schematic that we built,
Yeah.
X1 would be representing the
Yeah.
A0,
A0, B0, exactly.
Yeah, okay.
But we're going to have to define that logic in another module.
Yeah.
Exactly. So that means I'm going to need kind of a little internal wire placeholder for all of my potential Fs, just like we had before. And maybe to be consistent with what I was doing in the schematic entry, I will call this F00, F01, F10, F11. So I just created a few more wires here. Now the reason why it's not F0I00 is because we're actually going to use two multiplexers. So I'm not putting everything in one box anymore. So now I can put AND and call F0 the ANDing of not S0, not S1, and X1. And then I can do the same thing here. I'll say, or F00, I guess is what I said that was, F00. So then I can call this one, F01, will be the ANDing of not S1 and select 0. And then I'll AND this one, and I'll call this F10, and this will be not.
You need an X2 in that second one.
Thank you, comma X2. Yeah, so not S1. I'm going to be just as consistent as I can so I don't confuse people. I'm going to put X2 over here. It doesn't matter what order I put them in, really, except that the output has to go far left, but just to be consistent. So then AND F10 gets to be not S0, because that's 1, 0, so not S0, and select 1. And the third input would be X3. And then AND F. So I've got 0, 1, 1, 0, so the next one is 1, 1. And then that would be select 0, select 1, and X4. And then the last thing we need is to be able to sum all of those products together with an OR gate. So we're going to go OR, and F is the output, and then we'll say F00, F01, F10, and F11. Is it clear how that models exactly what we did in the schematic entry? All right. If you haven't done the schematic entry, do that first, and this will be more clear. Are there questions about what we've done before I move on?
Yeah, I'm just a little bit confused by what the select zero and select.
Yeah. So up here at the top line where it says wire 10 select, I've declared select to be a 2-bit wire. So if you were thinking in terms of like C, for example, you could think of it as an array. It's very similar, but physically, topologically, it's a bus. It's a wire that has multiple inputs on it, and only one input can be on it at a time. So I can reference which input I'm looking at, basically, by referencing it just like array notation. I'm saying, in this case, select 0, I'm looking at the rightmost bit. Select 1, I'm looking at the leftmost bit. So in our previous schematic, we had something that was like this. So I had S1, comma S2 as 2 wires. And now I'm just combining those to be that.
Oh, okay.
Does that make sense? Okay. Other questions? All right. Oh, you have a question?
Yeah, I'm just curious. Isn't this kind of redundant if we've done the schematic and this, or
Yeah,
am I
so
just missing
no,
something?
so this lab is to really just teach you all the different ways to do the same thing. In general, we don't use the schematic entry to create modules. And I think the reason why they have you do that first is because it's such a tedious process, so that when you get to doing Verilog like this, I mean, what took us an hour to do in a lab or a video, I took about 50 minutes to explain it. That's taken us 15 minutes to do with explanation inside of Verilog. And so it's just to show you how much simpler this is when you understand the syntax. Did that answer that question for you? Okay.
In this tool, create a schematic then, like from the Verilog?
Yeah, so not in the way that we did before. So it doesn't, well, technically, yes, you can do that too. I don't want to derail too much, but there is, and I'll get to it as soon as I compile this. In fact, let's go ahead and save this. And I'm going to have to go to my Lab1 file. So I'm going to change my hierarchy to files. My Verilog 1, I guess, hasn't been saved. So let me save that as Lab1. I think I don't know what I mean. But anyway, this needs to be lab1.b. You need to have, like I said before, you need to have one that matches your top level entity. So because if I'm looking in hierarchy, it says my top level entity is lab1. I need to have a lab1 Verilog file. So I'm going to go to module. I'm going to make a lab1 module lab1. Speaking of which, over here in multiplexer, I didn't name my module. I'll have to name that. And it's best to name them the same thing with the file. You don't have to, except for in the case of your top level entity, but it's best. So module multiplexer. Save that. Apologize for jumping around there, but I realized I missed that. So now in Lab 1, I'm going to do module Lab 1. And Lab 1 is going to be our top level. It's what will go onto the board. And so this is where we're going to get our A's and B's from. Does that make sense? This is where we're going to basically type those into the switches on the board. So we will have an output, wire, and these are also all going to be on bits. I can simply just say A0. Actually, you know what I want to do? I'm going to keep using the same syntax we had before. So to get you comfortable with this, I'm going to call it a wire. I'm going to call it A and B and F. That's a shorthand way of. I think that's a shorthand way. You know what? I don't trust it. I know think this works, but I don't want to go all the way through it and realize it doesn't work and not have that correct. So that's true. That's true. Trust me, throughout the course, you will definitely see me mess up. Yeah, there'll be plenty of those. All right. Input wire 1, 0, A, B, and so these are 2-bit. Except for this one is not an input. That's enough. Input wire A, input wire B, output wire. So inside this module now we want to create 2 instances of those multiplexers that we just built. And the syntax to do that is to write multiplexer, the full name of the module. So if you didn't call it multiplexer, if you called it mux or whatever you called it, that's what you would put there. So the name of the module, and then the short name. So you can think of this as type, like if you were declaring a class, right? So say this is multiplexer, and then I'll call this mux1, because I'm going to have 2 of these. And inside my mux, this is weird syntax, but this is how it's done. You do dot, and then x1 is going to be a 0. So you're going to do a dot with the parameter, and then parentheses for the value that you want to pass to that parameter. Dot x2, and this one's going to be called, let me think about it. No, that's not, we don't want to straight pass A's, well, do we want to pass, no, because we want to AND those A's and B's together, and I've forgotten that. So let's go ahead and do that first. So we can do that in our top level module. I think that's fine. If you want, we can create another module. Maybe that's good practice. Let's go ahead and create another module just for the practice. I think there are definitely people that would agree with you that the top level module should only have instantiations and nothing else, no logic. That's probably the best way to go. But don't ask me, because I don't do it in industry. I am trying to learn the best practices. I've got lots of books on the topic. Oh, I hit the wrong thing. So I'm going to go File, New, and choose Verilog HDL file. So what should we call this? We will call this module, and then we got a good name for it. You want to call it, I'll call it Lab Logic. That works. Alright, so Lab Logic is going to get us 1 bit of A. So input wire A. Whoa, accidentally hit the start button there. And input wire B. Because it's always going to be A and B, except for in the last case, where it's A and A. But the name doesn't matter as much as what we put in it. So we'll call it A and B, and then the last one we will put out as F, because I like F for my outputs. Some people do O's, whatever you like. And then same thing, I'm going to do an N module here. Alright, so the logic in the lab, and I'm going by memory here, you can look it up in the Lab1 manual if you want, but it should say that, let's think about it. It should get the multiplexer. If we're going to put the lab logic in here, then the lab logic should be the thing that gets the multiplexer. Because we don't know what to do unless we have it. We could use the lab to put all of our possibilities on a bus. We could try that. You want to try that?
Yeah.
All right. Yeah. All right. So we're going to use the bus syntax in that case. So I'm going to put output wire 3:0, because that's a 4-bit bus. So we're simplifying. Basically what we're doing here is we're going to simplify all of this logic into one single module, and we're going to put all of the possible outputs on one output. And then we will pass the correct ones into the multiplexer at the top level. So let's go ahead then. And we're going to create some gates. So the first thing we'll need is a few wires to store our outputs on. So we'll say wire, I'm going to say this is I0, I1 with commas, I2, I3, I3. So these are where I'm going to store my potential outputs. And for the first one, this is an and it's going to be the ANDing of A and B. So I'll store this on I0, and then I'll put A and I'll put B in here. The next one is going to be an OR. So this will be an ORing of, well, I'll put it on I1 as the second possibility, and it's going to be an ORing of A or B. And then the third one is equality check. That's going to be an XOR. And put this on I2, A or B. I3 is going to be not A. So then I3, I'll do a not, and that's just going to be not A. And I'll store that on I3, so it'll be not A on I3. And that was the third instruction. They wanted us to just complement the A bit. Questions on this part? It probably will make more sense as we start to use it, but are there questions right now? All right. And now I need to assign F. So I'm going to use one bit of structural logic here, not structural logic, yeah, assign logic or structural logic. I'm going to do assign F equals, and we'll do more of this when we get to the structural part, but this is the only way that I know of to put everything on one bus together. So assign F equals, and it's a 4-bit, so we're going to do 4 tick B. Is that the logic? Let me think about that. No. It's just going to be the curly braces. It's going to be in curly braces, we're going to put I0, I1, I2, and I3, like that. I maybe got that wrong, but I think that's the logic. We'll see if you get to have your wish and I get to make a mistake today. Alright, so we put all that on F. We've got those 4 bits now assigned. So this is now a 4-bit wire with the leftmost bit going from I0 and the rightmost bit going to I3. Now I have a question that I always have whenever I do this that I had to go look up, and that is, how is Verilog indexed? When I say 0, am I grabbing the leftmost or the rightmost? And I think it has to do, if I remember correctly, with whether I said 1:0 or 0:1. How are Verilog vectors indexed? I hope nobody minds that I have to go look this up. Alright. I love chip verify, by the way. It's super, super useful. Okay. 7:0. Bit selects. Any bit in a vector variable can be individually selected and assigned a new value. Left is 7, right is 0 when it's defined as 7, 0. If I were to flip these and do 0, 7, then this would be 0 and this would be 7. And that's what I thought, but I wanted to make sure. So from left to right, when you do it 7:0, which is the standard way, that talks about endianness basically, and this makes it, when it's on the right, that's little endian, because it starts, no, it's big endian. I can't remember. I'm not going to look up endianness. Go look it up. It's one or the other, but it changes the endianness of the vector. So when it's 7:0, the thing to remember is that the biggest number is farthest left, the littlest number is farthest right. So if that is the case, then that means that our I0 is the farthest left vector bit, which is, in this case, f:3, because that's how we've put it in. 0, 1, 2, 3. If that feels unintuitive, you can definitely swap these around and go 0, 1, 2, 3, and then you can reference them the way you'd expect. All right. So I'm going to leave it so I don't confuse people, but because it's I0, I1, I2, I3, then when I reference F3, I'm going to be grabbing the I0 bit. Does that make sense? Cool.
So it's just flipped, basically?
It's flipped because of the way that I put it in. Whenever I do a vector of 3:0 or 4:0, the highest number is the farthest left bit. And so since I put it in from left to right, that means I have to reference it from high to low. Yeah, so from left to right, so 3 would be I0, 2 would be I1, 1 would be I2, and 0 would be I3. If that's going to be confusing, I can swap these. I can do it from right to left. I3, I2, I1, I0. And now, because the highest bit is on the farthest left, I can reference it from 0 to 3 and get 0 to 3 instruction. So maybe that's the right way to do it. I think so long as you remember what you're doing, it's fine either way. But now we got to give this guy a name, and we called the module LabLogic, so we'll call the file LabLogic. Cool. All right. And we'll come over to Lab1. And we have our multiplexer that we haven't put any data in. And we'll need to have some lab logic. I'm going to call it LL1. And lab logic LL2. Oh, that was a 1. LL2. And I'm also going to do a multiplexer next to. Okay. So now we need some wires to store our lab logic on, and they have to be 4-bit wires. So let's go ahead and make a 4-bit wire. So wire 4:0. We will call this LOG1 for logic. Well, that's confusing because that's logic. I'll call it logic 1, comma, logic 2. You can call whatever makes sense to you. So I've got my lab logic. Now, I got to go back to my lab logic here. So it's A, B, and the output F. So, then in this case, we're going to do, for lab logic 1, these are going to be our A0s. So, our A0, B0s. So dot A is going to be A:0. Dot B is going to be B square bracket 0. And dot F is going to be logic 1. and that means that we're passing in A0, B0, and what we're getting out on that 4-bit vector, we're placing onto logic 1. And then we'll do the same thing with LL2, and this time it will get A1, B1. So do dot A, A1, dot B, B1, dot F, logic 2. Questions about that so far? Is that making sense? Good? Cool. So now that we've got our logic stored on our buses, we need to pass in the appropriate values into our multiplexer. So our multiplexer gets, I believe it's select, and then X1, X2, X3, X4, and it outputs on F. So for our first multiplexer, and I'm going to make a comment here, always good to have comments, this selects for F0. This selects for F1. And to be maybe more explicit, I'll say F:0 or square bracket 0 and F square bracket. And then up here I'll add a comment, creates or performs the logic given in the lab and puts output on logic 1. Both of those. Just a few comments so it's clear what we're doing. Alright, so now we get dot select, and that is going to be A, B, and F. We also are going to need our select to come in here. So in the top of our module, I'm going to add an input statement for input wire 1:0 select. Alright, so dot select is going to just be select. So not to be confused, this dot select means the select from the multiplexer module, and this select means the select from our module. The dot here indicates that this is part of the multiplexer module, or part of whatever module that dot is inside of. Is that clear? Do we understand that? So we got the dot select, so now we're going to do our dot x1, and that, because this selects for F0, then we are going to use the one that we put A0, B0 on. So that's going to be logic 1, 0. So the 0th bit of logic 1. I am recording this, by the way, so there will be a video as well. What? Oh, okay. Oh, I understand. Okay, no problem. Just wanted to let you know that it's there. So, all right, dot x2 is going to be logic 1. Dot x3 is going to be logic 1, 2. Dot x4 is going to be logic 1, 3. Okay, so what we're literally saying here, oh, we need to put the output as well. So let's go ahead and do that real quick as well. Let's say the output is going to be, so dot F would be F0 because that selects for F0. So what we're literally saying here is we've got this multiplexer, we're giving it its select bits, and that multiplexer will select between x1, x2, x3, and x4. And so what we're saying is that x1 is the 0th bit of our logic 1 vector that gets populated with this lab logic module, and x2 is the second bit, and so on through x4. So as long as we have our lab logic correct and our multiplexer correct, then our output should be correct. Okay. And we'll do the same thing from x2. And we'll just copy and paste these. And the select will be staying select, but everything else will become logic 2. Also, a neat trick on Windows, if you hold Alt or Option if you're on a Mac and click and drag, you can just do that. And then do it again. And add 2 if you want. Just showing you that's a fast way to do that. And then this goes on F1. All right. And then that should be the equivalent statement, if we've done everything correctly, that our block diagram was. Okay? Questions on that? Let's go ahead and compile that, make sure that it compiles.
Show you what you gotta do over here.
Oh, sure. Let's go back to that while that's compiling. I can look at on Lab1 module. Yeah.
So, if this is a multiplexer, right? You're supposed to simulate a multiplexer?
Yeah. This, well, we have 2 multiplexers here.
Yeah. But shouldn't one, if it has 4 inputs, shouldn't it have 2 switches?
If it has 4 inputs, should it have 2? It does have 2
Yeah.
switches. Select. Select is a 1:0 vector.
Oh.
So if we look back at our multiplexer, we said that select needed to be a 2-bit vector, and we got our not S0 and not S1 from our select bits here. And then so we just put select 0 or not S1, depending on what combination of zeros and ones we wanted for each.
Okay.
And then we ORed all of that together. Does that make sense?
Yeah.
Oh, we got some errors. So let's see, what did I do wrong? Oh, I forgot a comma. I forgot a comma on all of these. So your inputs, your dots need to have commas after them. Except for obviously the last one shouldn't have a comma. Cool. Save that. And compile one more time. Yeah, so we're making liberal use of the bus syntax to save us some writing. We could have done S0, S1. In fact, I think that's that comment I made down here. So we had like S1, S2, and that becomes select 1:0. Oh, more errors. What did I do wrong here? Expecting a square bracket on line 6.
You have a parenthesis on the end of that rather than a square bracket. On B dot.
Oh, thank you. Missed that. Did I copy that error down here? No. Okay, cool. Thank you for catching that. It would have taken me a minute to see that. Maybe 3rd time's the charm. Nope. What did I do wrong this time? We're getting there. 2 errors instead of 6 where we started. Dot where we're expecting a parentheses because I forgot a comma there. In one of these videos, I will teach you how to set up Visual Studio or Visual Studio Code to do code completion and linting for you so that you don't make these mistakes, because Quartus doesn't tell you when you've forgotten a semicolon or a comma. You only find out during compilation. There are tools that you can use to make that easier. It just requires a bit of setup, so I'll probably make a guide or something. Alright, now it's compiling. Great. And we can look with our RTL viewer to see if this looks about right by going to Tools and going to Netlist Viewers and choosing RTL Viewer. And we'll see a block diagram here, but if we expand all of our blocks and just keep zooming out to fit to window, to window again. And we can follow this logic and see if it seems right. So here's our A0, A1. Goes into, so lab logic 1 says we get the A0, B0, that's what that 0 there means. And those both go into this AND gate. Goes into this OR gate, A0, B0, or this OR gate, and also this XOR gate and this NOT gate. So we are getting an ANDing, an ORing, an XORing, and a logical NOT of all of our A0, B0s. And for lab logic 1, we're getting an ANDing, an ORing, an XORing, and a logical NOT for all of our A1, B1 combinations. And then those are going out into these multiplexers. And this multiplexer says that when we get zero and having a hard time seeing, oh, here we go. So the not 0, not 1. So that's not 0, not 1 for our select. Then what we should get is this AND right through here. And we get not 0 or not 1 and 0, so 0, 1. Then what we should have is this guy right here. You see how that's working? So I think this logic is correct. Are there questions about what this is and what's happening here? Alright. So the last thing to do would be to, well, we should write a test bench. How much time do we have? We do not have time to write a test bench today. Instead, I'm going to quickly show you the functional syntax. So I'm going to create a new Verilog HDL file, and I'll call this module multiplexer functional. And we'll just go ahead and copy the same inputs from our other multiplexer. that shouldn't be a problem. Okay. And we will still need our interim wires that we created for our multiplexer. These guys right here. Right. But instead of creating gates specifically, we're now going to create logic functions. So I'll say, for example, assign not S0 equals exclamation mark select 0. Assign not S1 equals exclamation mark select 1. Okay, I'm not going to go through the whole module here. We don't have time, and I want you guys to get some practice on your own as well. I will give you this little helpful bit of advice here, though. I will say an exclamation mark is a logical not operator. A tilde is a bitwise not operator. On a single bit, they function, on a single bit wire, they function the same. On a multi-bit vector, they will function differently. Same thing here, ampersand, ampersand is equal to a logical AND, whereas a single ampersand is equal to a bitwise AND. And that's the same story. On a single bit, they'll function the same. On a multi-bit, it'll function differently. And as you'd expect, here's your ORs. This is equal to a logical OR. And this one is equal to a bitwise OR. You have your XOR, which is the caret, and there's no logical version of this. This is just XOR. And then you have your XNOR, which, if I remember correctly, I believe is tilde caret, like that. And if you have questions or you want to know how to do anything else, there's a nice website under, it's on this website, I just can't, there's a search here. Verilog operators. And this will give you all of the operators that are available to use in Verilog. So paste that down there. And I will let you guys do the structural version, not the functional version, this version, on your own. Kind of work that through. If you have questions, ask me. And then next time we'll go through, we're going to go through test benches and simulation. Questions? Good? All right, thanks for sticking around. It is exactly 10:30. So, yes, you'll need a board in order to